Good evening, everyone. My name is Aveen Dayal. I'm a PMRF PhD student at IIT Hyderabad, and I'll be conducting the live session for the course Deep Learning for Computer Vision, conducted by Professor Vinny. And the idea or the goal behind these live session tutorials is to help you solve your assignment problems and also gain more hands-on skills on how to actually solve the problems in general related to computer vision and the course. So typically these live sessions are split into two parts. The first half we try to solve MCQ, numeric or fill in the blank type of questions related to the concepts taught in that particular week by the professor. And in the second half of the live session, we basically go through a code walkthrough and we discuss different libraries or different operations that you will be using in throughout this course. And in the last week and the last first 2 weeks, basically we started off with traditional computer vision techniques. Like initially, we started off with how do we represent images. Then we talked about different simple operations like flipping of the image, rotation of image. Then we talked about filters like convolution, cross correlation, then how histogram equalization works. Then we moved into slightly advanced traditional concepts like edge detectors, like Sobel edge detectors, Canny edge detectors. Then we moved into blob detectors, and then finally one of the most foundational algorithm called SIFT algorithm, which will help us identify key features in the image, and it is helpful in doing many applications like image stitching or object recognition, etc. So today we move in this week we basically move towards the deep learning part of computer vision. In the recorded lectures, professor has discussed about the foundations of deep learning, which is nothing but neural networks, deep neural networks. So it was the forward pass. What is a neural network? Then the forward pass in a neural network. How do you calculate the loss in a neural network? Then what is a backward pass in a neural network? And then the entire training happens through something called as back propagation, which is nothing but the backward pass. And back propagation depends on gradients. And then there is algorithms like stochastic gradient descent, which basically helps in updating the weights of the parameter using gradients and variants, other different variants of SGDs like ADAM, RMS prop, and ADA-grade, etc. Then it was also discussed about several different techniques to fasten to speed up the training process and also to help the models train in an effective way. So what are these training techniques like dropout, batch normalization, and yeah, pretty much these are the main concepts. So today we will basically solve first questions on these concepts and then we'll move into the coding part of these concepts. So like I said, we usually discuss question by question, and so this is the first very simplistic question we have. So the question over here is: consider a simple perceptron F such that it has four input features, that is why R4, and it is mapping to an output R. So this particular perceptron uses a simple activation function, which is tan h activation function. Now the input vector is this given vector 0.5 minus 0.7, 0.9, 0.3, and the corresponding weight vector associated with this input vector is also given. W is equals to this four-dimensional. The question is, compute the derivative of tan h of z, where z is nothing but a linear combination of weights vector w and the input vector x. We can ignore the bias term for now. So this is how a typical simple perceptron works, where you had a bunch of input features, we had their corresponding weights, and we did a linear combination of these inputs and weights, weight vectors. And the output is nothing but we call it as z. And then you send that z to an activation function. In this particular question, it is a tan h activation function. So the question is, what is the derivative of tan h of z? So typically, you can answer the question. I'll wait for a minute. If not, I can also discuss. Maybe let me just wait for a few seconds. If you can come up with some guess for the answer, you can post your answers in the chat. Maybe let me also explain. So let's start from the basic, like what typically happens in perceptron. Let's see diagrammatically. So let's say we have this input x. So typically this x is nothing but different dimensions are possible. So we have four dimensions, so four nodes I'm keeping for this x. And then we have another matrix, weight matrix, which is this weight matrix, weight vector for now. And then we have our output, uh, which is the linear combination of these two, which we for now let's call it z. So it is typically R4. If you see over here, in the question it is saying f is going from R4 to R. It means from four input nodes, it is going to one output node. And how is this input output connected? With the help of weights. So that is what this is. So each one W1, W2, W3, and W4. And similarly, X also is there, which is X1, X2, X3, and X4. Z is just one value for now, so we'll leave as is. So how the calculation of Z happens? Z is nothing but X1 into W1 plus X2 into W2, so on up to X4 into W4. So once you get this Z is then usually sent to an activation function in perceptron. So let's send this to an activation function. So in our case, what is the activation function? It is tan h of z. So this z then goes into tan h of z. So tan h of z. What is the tan h of z equation? Let me also write that. It's e to the power z plus e to the power minus z divided by e to the power z minus e to the power minus z. This is the equation of tan h of z. So we have all the values now given in the question. We just have to input these values, and then you'll get the value of tan h of z. But the question is, what is the derivative of tan h of z? So to understand the derivative of tan h of z, we have to usually compute the first derivative, which is nothing but the gradient of tan h of z. So I'll show you the final answer over here. So the gradient of tan h of z is 1 minus tan h square of z. So you can solve it basically. So, okay, I think the equation over here is slightly wrong. Let me just rewrite. So that it is e to the power z minus e to the power minus z divided by e to the power z plus e to the power minus z. So typically this is the equation, and then if I want to do the first derivative, I just keep on solving this equation. I can use the differentiation rule. Like if let's say there's a differentiation rule of u by v with respect to uh, differentiation rule of u by v is nothing but du minus dv by dv square, etc. I'm not very sure about the exact formula, but you can use the exact similar way of differentiation, and then you can finally get this particular output. So differentiation of tan h of z is nothing but 1 minus tan h square of z. And z we already saw how it is calculated. It is nothing but the linear combination of x and w, which is this value. Z is equals to 0.87. So just input z value in this tan h equation, and once you calculate, 1 minus of that square is the final answer, which is approximately 0.5086. So this is how the first problem is solved. So very simple problem. It's just you have to identify what are the input vectors you have, what is the weight vectors, how is z calculated, which is nothing but linear combinations. You also need to know what is the derivative of tan h activation function. So I hope this is clear. Any questions, any doubts in this first question? Otherwise, I'll move to the second one. Okay. So second is very simple. It's based on the concept itself. It's not a numeric problem. So I hope every you were able to go through the recorded lectures by the professor. So in that, professor has discussed a concept called as dropout. So maybe let me refresh what is dropout, and then you can take a guess what will be the correct answer. So typically, in your standard neural network or multi-layer perceptron, you have a bunch of neurons in, let's say, layer L minus one. This is layer L. And this is layer L plus one. This is somewhere in between. It doesn't have to be input output only. It can be somewhere in between also. And this is L minus one. This is L. And let's say this is L plus one. And we know that since it's multi-layer perceptron, every node in the previous layer is connected to every node in the next layer. So it will be something like these. Now, what does dropout say? Dropout says that you need to randomly drop some of these connections, intermediate connections. So we see the red lines, right? Those are nothing but the weights, or you can call it as intermediate connections between nodes, whatever you want to call it. So dropout says during the training phase, drop some of these weights randomly, but keep everything else in the network as it is. So, and then you do your normal forward pass, calculate the loss, and then do the backward pass. So this is a typical dropout mechanism. So based on this, try to answer which of the following four options are correct. And then we can discuss each option in detail, what is the logic or reasoning behind each of them. So let me pause for a quick few seconds. Try to guess which is the correct option and post your answers in the chat. Just take a informed guess also. You can take a guess because I just told you what dropout does. Okay, the guess is A. No, it's not, because it does actually the opposite. It doesn't cause the network to overfit. It actually helps the network. It prevents the network from overfitting. Okay, let me just discuss each option. So, what is the idea? You understood what is dropout. That you're dropping randomly some red connections, which is there in the figure. Now, what are these red connections? These are weights. Now, what are weights? Weights are the most important thing in any neural network. It is these weights which will define whether the problem is whether the model is solving the given task or not. If the weights are not good, then the model will never give a correct output. Okay. Now, if you're saying that you're randomly dropping weights, it means somewhere you're randomly dropping the model's representation or problem solving power also, right? Because weights are the ones which actually solve the then. But why are we doing this? Because typically in these neural networks we have huge number of layers. So we have like even 20, 30, 50, 100, 150. A lot of layers are possible. Now when you have some simple problems to solve and you have big networks, then the model will overfit to these problems. So when I say problems, in the sense, let's say if I have a training data set, let me write it down. Let's say if I have a training data set of just 100 samples. Okay, so it's a relatively small data set, but I have a very big model. Let's say my model has around 50 layers, 50 mlp layers. Okay, hidden layers. Now immediately the model will start overfitting, because what is overfitting? Overfitting is nothing but rote learning, or we all say by heart, right? If whenever a student tries to learn something, the teacher or professor usually says, don't by heart the answer, try to understand how the answer is coming from the question, like reason out the process, don't just by heart. So typically overfitting, you can understand it to be like a model by hearting what is the input, what is the output. It is not actually learning which features inside the input should I check or should I look at to actually give the output? It will just by heart that okay, if I'm getting this type of input, this will be the output. That is very bad because when you move into real world, when you deploy this model actually in the real world, then the model will fail very drastically. The performance will be very bad because the model never learned how to solve the problem. It just by hearted what will be the input pairs, what will be the output for that particular input. So this is why overfit. This is what is called as overfitting. So one way to check overfitting is if your training loss is very low, okay, and your test loss is very high, not test, validation loss. Your validation loss is very high, then it means your model is overfitting. Why? The same concept, right? If the training loss is low, it means it is by-hearting whatever given input, because in training output is also present, right? So given an input output pair, it is learning, okay, this input will have this output, but it is not actually understanding the problem. That's why validation, since you don't have the output pair, it only has input, it doesn't know what to give as an output and it will be bad at it. That is why the validation loss is high. Another way to check whether a model is overfitting is another metric to look at is training accuracy. So if your training accuracy is very high, but your validation accuracy is very low, then you can again say that the model is overfit. So typically to avoid overfitting, one way is you can reduce the number of layers. Okay, I don't want to use 50. I'm using, let's say, 30. But even after using 30 layers, then the model starts to underfit. What do you mean by underfit? That even the training accuracy or training loss is also high. So that will happen when you start reducing the number of layers. So then what people say, okay, let's not go to 30 layers. Let's have 50 only, but instead use these techniques like dropout. So by doing dropout, where we randomly drop these layers in between, we are forcing the model effectively reason and understand how to solve the problem rather than just by heart. So now let's move into how is by hearting connected to weights. So like I said, each weight, all these weights are important to solve the problem. So if it's by hearting, then typically, let me highlight with another color. Let's say if given an input pair and there is an output pair during training. So if a model is by hearting or overfitting, typically it will happen that some of these edges will have uh, like high non-zero values. Remaining all will have very close to zero values, like the one I'm highlighting. Similarly, in the others also like this, something like this. It'll be very few small subset of these values. So only on these particular highlighted edges, all of the weight is focused. And this is what is happening. This is what we call as one of the ways overfitting happens, because your only few weights are actually working in giving the output. It's not actually reasoning the problem. It's just by hearting, by looking at these weights. If given this input, this will be the output. Now, if in dropout, these highlighted weights are dropped, then the model is now forced to actually think about, okay, what should be the other alternative ways to solve this problem, and then it will start looking into other alternative ways to pick, well, okay, this might actually solve the problem, or this weight might actually solve the problem, and etc. So that is why by doing dropout, by randomly dropping these connections, you are forcing the model to put more pressure into looking at all the weights that are possible and actually pick the weights which will solve the problem. Okay, I think enough of concepts. Let's discuss these solutions. First one is wrong directly because it does not cause overfitting. This is a problematic. It does not cause overfitting. It in fact prevents overfitting. Second point is during training with dropout, the network adjusts the activation levels so that the outputs remain consistent and dropout is not applied during inference. This is true because that's what I just said. Because we want to drop such that the other activation levels, other weights will work properly, and it will make sure that the outputs remain consistent with or without dropout. Third one, dropout during training leads to smaller final model size as some permanent connections are permanently removed. This is the wrong word over here. Permanently, nothing is permanently removed. It's just randomly some weights are dropped for that forward pass. In the next forward pass, some other weights are dropped, but there is no permanent removal of anything. So again, this statement is wrong. The fourth statement, the final output during training when dropout is applied is multiplied by the dropout rate to maintain the expected output when dropout is not applied during inference. This is again true. So there are subtle implementation details over here. So you try to apply some weightage multiplication terms during the during the testing phase, inference phase, to balance for the dropout that was done during the training phase. So this is why D is also correct. Sorry. I think D, okay, oh, one small thing, it is not multiplied by the dropout rate actually. My bad. It's actually, the answer here is not actually multiplied by the dropout rate, but it is 1 minus the dropout rate. So that is why usually we multiply 1 minus the dropout rate, but here dropout rate itself, that is why this is wrong. So usually you multiply with 1 minus of the dropout. So the correct answer is only B. Okay, any doubts, any questions in this particular problem? If not, we'll move to the third one. So let's come to another concept of regularization and batch normalization. Again, these are techniques that are used to boost the neural network training and performance, overall performance. So here you have four statements, each of them corresponding to L1, L2 regularization and batch normalization. Try to pick which are all the correct statements given out of these four statements. So maybe let me quickly pause and then we can discuss in detail about all these four statements. You can post your answers in the chat. Let me discuss. So let's first discuss the concepts itself. Yeah, I think this diagram helps you understand. So L1 regularization, it looks something like this. So before even going to this diagram, let's see what are we trying to say. How is an output calculated? Let's see, y is the output equals to some activation function. I'm saying let's say sigmoid of w1 x1 plus w2 x2 and so on up to wn xn. It's a very simple MLP over here. It's not a complicated MLP. Very simple one hidden layer MLP we're using. Now, in these are the important terms, weights which are being learned by the model during the gradient descent and backpropagation, etc. Now, sometimes during the training, what can happen is maybe in some iteration during the training process, some of these weights might start getting very high values and some will get very low values, like close to zero or very almost negligent values. Close to it means that there is no point of having those weights at all. Now, this is again similar to what overfitting is, right? Because you're having only certain weights with very high priority, certain other weights have no priority at all. So how do we avoid this? One way is dropout. Another way is regularization. So what regularization says? Okay, so when you're having, when you're calculating the loss is nothing but L is equals to chill ground truth. Let's call this y hat. Y minus y hat. Let's say we'll say use a simple squared loss. So if you want to expand on this, it will be something y minus this equation which we have, sigma w1 x1 so on whole square. So this is typically the loss. Now when we want to add some constraints on this, what do we say? We do plus some lambda times, this is some constant factor you can ignore for now, lambda times weight vectors norm. So what is this weight vector norm constraint will do is basically it will not let any one particular weight to have a very high value. It will always make sure that all of the weights have close to values or similar values. Not one particular weight is having very drastically high value. So you can use L1 norm over here, uh, or you can use L2 norm over here. So actually it is L2 norm or etc. So by doing this, we are basically saying that no one particular weight will have a high value, and because of that, we are now able to reduce the overfitting. So to look at it illustratively, that is what the figure which you see. So the axis, let's say this is W1 and W2, only two W's you have. So now, because we are constricting that the W1 and W2 should have either L1 norm, then it will form something like this diamond shape. L1 regularization, basically that vector norm, this W1 vector L1 norm of this vector W will form this rhombus shape when you visualize it in 2D space. So now we are telling that this loss curve, which is this value, should will come to zero at any of these W values which is close to here. So not a lot of the values are having drastically different values. It is very constrained space. In this particular space only, you will have to bring your loss to zero value or minimal value. So now we are saying that neither W1 nor W2 can go to an extreme length. It will always fall somewhere within this space. So the rhombus shape is L1 norm. If you do L2 norm, you'll get this circle which I just drew. So typically it will look something like this. Let's do properly. It will be the same thing, but it will connect the edges, circles. So this will be L2 regularization. So in this way, we are basically constructing that not one of the weights will go very high and all of the weights will have equal priority because we don't want to overfit the model. So these is L1 and L2 regularization. Now coming to batch normalization. Batch normalization says that let's say we have these some hidden layer L. Now typically training happens in this mini batch concepts, right? So each of that mini batch will enter. Let's say if I have a mini batch B1, this will come to this layer L, and then after they'll calculate some output. Let's say we're calling OB1, which is the output for mini batch 1 from all the nodes in the layer. Now let's say B2 also comes in, second batch. Correspondingly, OB2 comes. But because B1 and B2 are coming one after the other, there is a chance that the ranges of OB1 and OB2 might be very far away. So that when the ranges are very far, of ranges as in the what do you say, the minimum and maximum value that is present in OB1 and OB2, you can consider them to be ranges of sorts. So idea over here is since they can be of very different values, the training will take a lot of time. Normalization basically brings all of these values into this standard normal distribution with mean 0 and this is a standard normal distribution, mean 0 and deviation 1. So it tries to bring across different batches B1, B2, B3, try to normalize all of them to standard normal curves. Because of this, again, some sort of speed improvement is seen during the training time, and also you observe some type of overfitting is also reduced when you apply batch normalization. So this is the concept of batch normalization. Now let's look at the options. First one says batch normalization cannot be used together with L1 and L2, which is not true at all. Batch normalization is completely doing different things than L1 and L2 is doing. So A is wrong. Second says L1 regularization can lead to sparse weights, which means many weights are zero. That is true because if you look at the figure, right, the rhombus, when if you want to touch it, this value at zero at this particular thing, when the loss is touching this particular rhombus, immediately it will touch at the edges, and when it touches at one of the edges, the other particular weight will become zero. So what I mean by that is if the loss is touching at this particular value, that is the closest it can touch this particular rhombus. That's the first time it will touch this rhombus. As soon as it touches the rhombus at this point, W1 will have some value, non-zero, whereas W2 will become 0. So this basically the L1 norm can L1 regularization can make some of the weights to go to 0, sparse weight matrix. So B is correct. C says batch normalization normalizes the inputs of each layer by subtracting the batch mean and dividing by batch standard deviation. This is correct, but the last point is the last sentence is wrong. Slows down the training process. That is wrong. It doesn't slow down. In fact, it helps speed up the training process. So that's why option C is also wrong. So what is the correct option still now? B is correct. C is wrong. And D says when using batch normalization, it is necessary to disable it during the inference phase. So it is true. This statement is also true of sort because you technically don't completely disable it, but you don't calculate the mean and standard deviation of each batch. You basically have some running mean, running standard deviation values. So again, that is a slight implementation, but typically you can also, in very simple terms, say that okay, you're disabling it during the inference phase. You're not technically calculating batch mean and batch standard deviation. So the correct answer is B and D. Any questions? Any doubts? If there are no questions, then let's go ahead to the next. If there are no doubts, let's go ahead to the next question. So this particular is again a numeric problem. You might see some. So basically, all these are like sample problems, like plus problems. You might find similar assignment questions for similar type of problems like these. So this is based on the RMS prop optimizer. So this is a variant of stochastic gradient descent, which is which RMS stands for root mean square propagation based gradient descent. That is what RMS prop stands for. So given these all values, like the new theta, given all the other values like old theta t value, gradient of theta t, gradient accumulation RT minus 1, learning rate, decay rate, and a small constant, we need to calculate what is the new value of the parameter theta t plus 1. So let me quickly pause for a few seconds. It's if you remember the formula from the lectures, then you can easily solve this problem. You have all the values with you. You just have to put it in the formula and get the answer. So it is very important that you remember the update equations of these optimizers because those are very fundamental. So it's always better if you remember these. So if you know the formula, let me pause for a few seconds. You try to post your answer in the chat. Okay, let me try to show you the equation and let's see. So this is a typical equation. This is a standard equation for RMS prop. Maybe let's understand what this equation is doing. Then we can go to how just putting in the values and solving the problem. So a typical loss, how does it look like in two dimensions if you want to visualize? Let's say this is one type of a loss. So let me draw it properly. And the lowest point or the minimum point is, let's say, in the center of this loss curve. So this is where you want to be, because that is the lowest point. And what is this space? Imagine this space to be nothing but all, it's a two-dimensional space, right? Let's say this is like W1 and W2. Usually in your typical neural network, this is a very high dimension space, but for visualization, I'm keeping it simple. Okay, so typically you start off somewhere random because you do random initialization of W1, W2, so your loss will be very high. So this is the loss curve basically, by the way. This is nothing but how loss surface looks like. Okay. So you're starting off some random point, which is the black color point, and you want to come to this yellow color point in the between. That is the agenda, or that is the objective of any uh, gradient descent algorithm. Why? Because when you come to this middle orange point, that is where your optimal value of weights will be, which will help you solve the task. That is the idea. Now, the simplest gradient descent, what it will do, it will keep on updating, right? Like it is, if you remember the gradient update rule. So, what was the gradient update rule? Wt plus 1 is equals to Wt minus learning rate times gradient of Wt. This is a gradient rule. So what does it mean? At every time step, the vector W keeps on moving either in each of the directions. Both W1 and W2, both of them will move. So in a typical SDD, the curve look like something. It'll go up, it'll go down, it'll go up, it'll go down, it'll go up, it'll go down, and so on. It'll reach the center. While this is fine, problem with this is, if any human sees this figure, there is no point in going up and down, up and down, up and down when you know that the model should ideally just go in a straight line, because this is the most simplistic way to reach to this center. Why are we going up and down, up and down, up and down, wasting a lot of training steps? Now, that is a problem which people observe, especially in these scenarios, when the vertical axis is not changing much. The horizontal axis, the horizontal direction is changing a lot, but the vertical direction is not changing in minimizing the loss. Why should we waste the number of steps by going up and down, up and down, up and down? So, this is a problem with SGD. Then people suggested, okay, how do we avoid this? Then people have come up with different variants of it. So let me write down what are all the variants. The first variant they came up with was momentum. Then they came up with adagrad. Adagrad. It's called adaptive gradient. Third, they came up in RMS prop, which is this particular problem. Fourth, they came up with ADAM, which is ADAM is right now the most go-to or the most popular optimizer for most of your standard deep learning models, including your big LLMs. They're all built on top of ADAM or variants of ADAM. So SDD had a problem. Momentum solves this problem very nicely. Momentum basically says keep track of previous gradient updates, and if you see that the gradients are changing its direction, like if it's going up once, then it is going down, and it means that in the vertical direction gradients are cancelling out. So if the gradients are cancelling out, then by keeping track of the previous gradients, you calculate what is the most movement happening in which direction, and you move in that direction. That is the idea of momentum. So that is why momentum optimizer is can solve this problem simply and go into the center. Now, adaptive gradient says that in how do we, because this movement of going up and down is also a factor of this learning parameter alpha learning rate alpha. So the bigger the learning rate, the bigger jumps of up and downs will be. So it says, how can we have a different learning rate for each of the weights? Because if we had small learning rate for W2, jump in the up and down direction will be small because alpha is small. Similarly, if you had high alpha value for W1, then the movement in the horizontal direction will be much bigger. So that is where it says, how can we have these alpha values adapt to different weights depending on the loss surface we have. So there was a simple way. So Adagrad uses a very simple. So whatever equation you see 1 and 2, Adagrad also uses similarly. Only difference is it doesn't have these parameters. So these things are not present in Adagrad. These rho and 1 minus rho. Everything else pretty much remains the same. RMS prop then came up with an idea of having these values rho and 1 minus rho kept inside. Why? Because if you don't keep row and 1 minus row, you're not keeping a cumulative proper exponential averaging of all the past values. Instead, you're giving equal weightage to all the past values. But RMS prop said don't give equal weightage to all the past gradients. Give an exponential weighting what's the priority. So exponential weighting average basically gives more priority to recent past and less priority to more previous past. So that is the difference between ADA grade and RMS prop. So I hope that is clear. Now, if that is clear, the two equations we just have to understand. First one is keeping track of all the previous gradients, RT. And now when you're updating the parameters, you just scale your learning rate by root mean square, right? That's why it is under root RT plus some constant, small constant value delta multiplied by the gradient. So these terms, right, which I'm highlighting in green, these look very similar to your SGD, standard stochastic gradient descent. Only difference is this bottom part, which is scaling your learning rate. That is what RMS prop is saying, and this RT is coming from the above equation. Okay, so if this is clear, then you have all your values with you, RT minus 1, theta t, delta theta, rho values, everything. You just have to substitute all these values and you will be able to solve the problem. Okay. Any doubts or any questions? Okay, then let me move ahead to the next one. So question 5, again, it's based on the same gradient descent concept. It's a simple problem. It's basically 5 statements are given on these gradient descent, and we have to figure out which are the correct statements. So let me explain, let me read out each of the points. Let me first explain the concept of these. So we saw these loss curves, right? We saw how you can update the gradients and move towards the loss. Now there are different ways to again do the update also. Now how can we do the update? We can actually do a complete batch gradient descent. We can do a mini batch gradient descent, or we can do a stochastic gradient descent. So why are we doing these three different things? Let's look at it. So typically your data set, which I'm calling it as X, if your data, there's a limitation on how much data you can load at a time in your memory. Okay, that is the typical problem. Like we all have RAM, GPU RAM, right? Typically it goes around, standard GPU RAMs are 16 GB to 48 GB. There are bigger also, but those are more expensive. Typically this is the range of RAM. But data sizes nowadays are in the order of 100 million, 1 billion. Nowadays 1 trillion is also there. And each of these data, again, 100 million means it can easily be some, I think it'll be close to 100 GB also, and so on. It'll be like a lot of huge data. Now when we're calculating the gradient weight update, right, using gradient descent, what is that? WT plus 1 is equals to WT minus alpha into gradient of WT. Now this gradient, and we do this across all the samples basically. Now, typically batch gradient will do across the entire batch. It means it should take into consideration all this 100 million samples. It means it should try to fit all this 100 GB data into the RAM, because then only it can calculate this update of across all the samples. But it is not possible because the RAM is limited. It is only 16 to 48 GB. So how do we avoid this? That is what people said. Okay, let's break the data into small chunks called batches. So that is where this mini batch concept came into picture. Instead of loading your entire data set on RAM, load small batches of data into the RAM. And now in that small batch, you update the WT using that small, you update this WT T plus 1, sorry, WT plus 1 using the small batch. And that is where you get mini batch concept. Stochastic gradient kinds of takes it extreme level. It says update your WT after every sample. So that is the most extreme case of mini batch gradient descent, where if you update the W values after every sample, that is stochastic gradient descent. So how is it different? If let's say if I'm having an entire data with me and this is my optimal loss, which is the center, And if I'm updating my W at one point in one go, I'm looking at the entire data set and I'm saying, "Okay, okay, this is the most optimal point." You come jump directly and you keep moving straight forwardly towards this minimum point. So that is why the each gradient is a straight line. There is no variation, there is no misinformation because it is looking at the entire data. So the update is as accurate as it can be, the gradient update. That is why you see straight lines towards the minimum. But if you see only small mini batch is nothing but one particular chunk of your entire data set. So the chunk will only be representative of one part of the data set. It is not representative of the entire data set. Then what happens? Then you that's why you see some wonky like this wavy path, right? Sometimes it goes up because it estimated wrongly based on that particular mini batch. Then it goes down because it estimated again wrongly based on this mini batch. It goes up again, goes down again, and finally reaches. And this is why mini batch gradient descent is like slight variance you can see because it is just looking at one chunk of the entire data. Now, stochastic, like I said, is the extreme version where it looks at each sample and then updates the model. So it has very high variance. So that is why it has more up and downs, up and downs, up and downs till it actually reaches the output. So this is the three different concepts of batch gradient descent, mini batch gradient descent, and stochastic gradient descent. Now, given these concepts, try to identify which of these statements are correct. I think I already shown the answer. Okay, let's go ahead and discuss each of these statements. So, what is the first statement? Batch gradient descent can lead to memory inefficiency when dealing with very large data sets. True. That is what we just discussed. Memory inefficiency is possible when the data sets grow. Second, SGD often leads to noisy path towards convergence but can help model escape local minima more effectively. So, is this true or wrong? Noisy path, yes. Can it escape local minima more effectively if it's noisy? Any guesses? Yeah, it is true actually. And then the third point comes mini batch gradient descent is always faster in terms of computation time per epoch compared to batch gradient descent. Typically, it is true, but this problem over here is the word always. This is not actually true. What if the mini batch gradients and batch gradient descent have the same size, right? Like, then if the data set is small, it doesn't make sense. So that is why this statement is false. Fourth says stochastic gradient descent guarantees faster convergence to the global minimum compared to batch gradient descent, mini batch gradient descent. This is wrong. It doesn't guarantee faster convergence. In fact, it can take more time because it is very noisy. It can take more time. So this fourth statement is wrong. Fifth says using a smaller mini batch size and mini batch gradient descent generally increases the variance of the parameter updates. This is true because the extreme case you remember, right? If stochastic is the most noisiest, up and down, up and down, up and down, up and down. So anything between mini batch and stochastic, as and when you go from mini batch towards stochastic, you're increasing the variance constantly. So that's why whenever you keep on increasing the mini batch, you uh, you keep on increasing the variance. Okay. Sorry, not increasing the mini batch, but as and when you decrease the mini batch, you keep on increasing the variance. So correct statements in these five are 1, 2, and 5. Okay. Any doubts in this particular question? Okay. If there are no doubts, let's move to the next question. So this is again based on a very simple augmentation strategy called mix-up. So given this particular neural network is using a mix-up augmentation, mix-up typically uses two pairs of input. What is an input pair? Input pair is nothing but x1, y1. That is like one input output pair. Similarly, mix-up usually uses two input output pairs. Is there a question? Okay. Please mute yourselves if there are no questions. If there are questions, please unmute and ask. So typically, mix-up consists of two input output pairs. This is one x1, y1 and x2, y2. their values are actually given with us. And there's a hyperparameter lambda with mixup. Now the question is how uh, what is the mix-up augmented sample X mix and Y mix given these are the input output pairs. So let me quickly pause for a second, try to solve this. I hope you were able to watch this in the lecture videos. Very simple formula, it's nothing but convex summation of input, both of the input pairs. I gave you a very good hint, convex summation. So let me quickly pause for a second, post your answers in the chat. After that, I'll discuss the answer. Let me discuss the solution. This is a simple formula. X mix is nothing but lambda into x1 plus 1 minus lambda into x2. Y mix is nothing but lambda into y1 plus 1 minus lambda into y2. Nothing else you have to do. You are given the vectors with you, both x1 and y1, x2 and y2. You just have to calculate, and this is the answers you get. X mix is 0.626139, y mix 0.3, 0.7. So what is the idea of these two things is basically typically what mixup says is it's an augmentation strategy, right? Why do we do augmentation strategy? Whenever you have less number of samples, then we typically say, okay, we need more. We like whenever there's less number of samples, there's a problem with model overfitting, model underfitting. A lot of issues happen. To avoid all these problems, people say collect more data. Sometimes it is easy to collect data, but most of the times it is very hard to collect data. That is where augmentation helps us. Augmentation, basically, there are different strategies of augmentation, especially in computer vision. Let's say this is an image. Okay, there is some object, let's say like a person is also there. Now, what are the different possible augmentations you can do? You can maybe reduce, increase contrast, slightly rotate the image, add some Gaussian noise, change the colors, color intensity variation basically, uh, crop randomly small parts, like some parts you can just crop this part or this part or etc. Bunch of different augmentations are possible. Just like all these augmentations are possible, mix-up is another very powerful strategy. It says if you're given, because you can always represent all these image samples as data points in vector spaces, right? So let's say this is one data point which I have of x1, and if I have another data point x2. Now, if you have these two data points, it says if you join these two lines, they can be here. All of these are nothing but interpolations between these two things, right? Like x1 and x2. In these straight lines, all of these points over here on this straight line will be some variations of this x1 and x2 combined with each other. Now, how to get each of these? That is where this lambda parameter comes into play. So if I say lambda is 0.3, then it is somewhere closer to x1, the output sample. It look closer to x1 than it is closer to x2. As and when you increase lambda, it will start looking more and more similar to x2. So now with this idea that of having different lambda values, you can get a bunch of new samples. So previously, originally we had just two samples. By varying lambda, we can get like a lot of samples now. We can increase this new samples will be much greater than 2. So this is one way to increase your data pool or training data set. Why? Because it will help your model train better. That is the idea between mix-up augmentation. Okay, any doubts in this question? I think there's a question. Yeah, all these recordings will be available online. So all of them are uploaded to a Google Sheet, and the Google Sheet link is present in Swayam portal. So that should be that you can check from there. Yeah. Apart from that, any other doubts in this particular question or any other question which we discussed today? If not, then let's move to the coding part of today's live session. So I hope you were able to look at the NumPy library. And yes, last week we also discussed about the different image libraries like skimage, Matplotlib, Pillow, CV2, those libraries also. Please do if you did not, because those will be very helpful. Today we will move into slightly different library called PyTorch. So just like how NumPy creates arrays and tensors using NumPy arrays, NumPy tensors, PyTorch also creates its own tensors, and PyTorch is more friendly in creating neural networks. So that is one library again in Python, that is Python compatible. It will basically create neural network models, all these big neural network multi-layer perceptrons and all these functions like, sorry, how do you calculate the forward pass, like the linear combination of inputs and weights, and how do you calculate the loss, how do we do these back propagation. Ideally you can do all of these things in NumPy, but PyTorch will help you write all of these things in a very few 1 2 3 line, like few simple lines of codes. So that is why PyTorch is helpful, because it will abstract away all the minute operations that you would need to write if you're using another library like NumPy or etc. Some other smaller library. Okay. That being said, let's move into the workings. First, let's, since it's the first introduction to PyTorch class, I will keep it very simple. We'll first discuss what are the bare minimum tools, or what are the bare minimum elements present in PyTorch. How can we modify these tensors using some standard operations in PyTorch. Then we will discuss and create our very first neural network. And then we'll also see how you can create a neural network in NumPy, how you can write everything from scratch if you ever want to do that, or you can use PyTorch. First things first, like I always say, import all your statements. That is the most important thing, because that will help you not worry about any of the errors, import errors that will get in later. So the first one's import time. This is a standard Python library which keeps track of your system time clock basically. Then you have random option, import random. So this will basically help you generate those random distributions, random vectors. When we say let's initialize the weights randomly, how do we do? This is where this random function will come. Then NumPy, I think there is enough introduction in the last 1 2 classes. NumPy is a very powerful library which will help us create NumPy arrays or tensors, and we can also solve a lot of linear algebra problems within few lines of codes. Pandas is again a library which is used to deal with CSV type of data. Now, what is a CSV data? Everyone must be aware of Excel sheets, right, or Google Sheets, Excel sheets. So typically, those sheets have for their representation as comma separated values or CSV. So those type of sheets can be uploaded into Python using pandas, and then you can do all the operations which you do in Excel, right? And any more advanced database operations which you want to do, like SQL query, or like merging two Excel sheets, or finding common points in these two data, etc., etc. All of these will be done by pandas library. Then Matplotlib, like we discussed last week also, Matplotlib is used for visualization of plots, linear, like your standard line plots, bar plots, and you also have your scatter plots, or you can also visualize images too, which we saw in the last week session. Now let's come to today's PyTorch libraries. Import torch. This is the most fundamental import statement that you need to use. This will basically load the PyTorch library into your current environment. In PyTorch, there are again several different classes which are present. So don't worry if you don't know what class means. You can think of these to be functional tools or something. So import NN. NN stands for neural network module. So this particular neural network module, using which you can create your entire neural network architecture itself. Then there is something called as data sets. So data sets, basically like the name suggests, it will handle all your data sets, which either you can upload your custom data. If you are uploading your custom data, you have to make sure to arrange your custom data in a certain format that was acceptable by this dataset module, and you can upload your custom data. Or dataset itself has a lot of existing datasets present with it, which you can download and run your models. Then there is data loader. So data loader is where you see the mini batch gradient descent, which we do, right? How do we create those mini batches? Like, given a particular batch size, how do we split the entire data set into mini batches? How do we load these mini batches during the training one after the other? Once it's done, how do we send it back? All of these things are handled by data loader module from PyTorch. And then this two tensor, it's a simple broadcasting for now. Don't worry, I will explain what does two tensor mean. So a fundamental unit in PyTorch is called as a tensor. Just like how NumPy has arrays, PyTorch has tensors. Now tensor can be anything. In a actual mathematical definition, a tensor is any entity or object which has greater than 3 dimensions, but greater than or equal to 3 dimensions. But in PyTorch, you can ideally, people very loosely talk about one-dimensional tensor also, which is nothing but a vector. If it's one-dimensional tensor, it is nothing but a vector. If it's two-dimensional tensor, it is nothing but a matrix. So just like how we did create an array, two-dimensional array, one-dimensional array, vector, and tensor, all of these things can be created in the PyTorch tensor. So how do we create tensors? Tensors can be created either from the list. It's very similar to how we create NumPy arrays. We can create it from a list, we can create it from a tuple, or we can create it from another NumPy array also. So these are the different ways possible in which you can create a tensor. What is a command? We just write torch.tensor, and the input will be either a list or a tuple or a NumPy array. Any of these things you can give, and this torch.tensor will convert those things into a tensor. Very important to do that, because if you give a NumPy array thinking, oh, it's a similar two-dimensional array which is there, why do I have to convert to tensor? It won't work, because PyTorch is built only for tensors. You have to convert to that particular data type to use all the PyTorch functionalities, otherwise it won't work. Okay. So this is how these tensor looks like. Tensor ABC, I just printed. Whatever we wrote on the top, that is getting printed. Now, just like how NumPy had some standard operations, or what's the standard ways to create certain arrays, right? Tensor also has some standard operations or tools to create certain standard tensors. Like what? Torch.ones. It, like the name suggests, it will create a tensor of all ones. All the elements will have one value, not one value. It will have the digit one value. So, and the shape you specify 5 comma 3. So create a two-dimensional tensor of the shape 5 comma 3, and all of the values will be the digit 1. You can see in the bottom. Similarly, torch.zeros will create nothing but a tensor of the size 2, which is a one-dimensional tensor. And then this particular two values will have just the value 0. Now, another interesting is empty. So usually when you don't know what values to give, but you know what is the size of the tensor you want, that is where you can give empty. So that will basically create some random values inside, and it will give you the shape which you want. That is what you see in the bottom. You can see a lot of similarity between tensors, PyTorch tensors, and NumPy arrays. So that is actually true. A lot of operations, because both of them, like I said, fundamentally are dealing with the same array structures, tensor structures, right? So they have a lot of similar tools or operations that can be done. But subtle differences will be there in how you call them. Just make sure that each of the differences. NumPy has subtle way of calling certain operations and tools. So PyTorch has a subtle different way. Okay. Now, if you want to create a uniform distribution, you create torch.rand 1 comma 3. Now, remember, similarly for normal distribution, torch.random 3 comma 4. So what is this creating? This is creating a tensor of shape 1 comma 3. All the values are coming from a uniform distribution between that uniform distribution ranges between 0 to 1. Similarly, normal distribution, it also creates a tensor of the shape 3 comma 4. Values are coming from a sample of a normal distribution. Now, why is this important? If you think about it, if you A and B can be now vectors, weight vectors, which you use in neural networks. If you want to create a weight vector of 3 comma 4, weight matrix of 3 comma 4, you can just do the same thing, torch dot rand 3 comma 4. You're initializing your weights randomly. This is a simple way to do that. Okay. Then similarly, there are other operations called like zeros like rand like. So what it creates is it creates a tensor of the shape A, but all the element values will be zero. Similarly, rand like basically says it creates a tensor of the shape C, but the values will be coming from a uniform distribution, which is the same, right? Which we just created torch dot rand, same like that. This is how the outputs look like for each of them. Okay, let me quickly pause over here before moving on. Any doubts, anything that is unclear until the basic tensors which I just discussed? You can post your questions in the chat or you can also unmute and ask. If it is clear, then let's move ahead. Next comes reproducibility. How do we ensure reproducibility of neural network models? Very fundamental concept. Everyone needs to remember, or like if you're entering into data science or AI, ML, this is a very important concept because n- recently with these LLMs and everything, more and more reproducibility is getting lost. So it's why is reproducibility important? Because if you want if a person or any organization is saying that I have developed a very good deep learning model and I am achieving so and so level of accuracy or performance, whatever it is, in certain types of tasks. Now, ideally, any person using that model should also, if he wants to create from his own, when he's creating the same model which the other person has created, he also needs to get the same level of performance in those tasks. But since fundamentally all these neural networks are built on random weight initializations, you can quickly see that since it's random weight initializations and we run it only for like 50 epochs, 100 epochs, how many number of epochs, it might be possible that by the end of those epochs, we might not get the same level of performance as the first person who was able to do that. Now, how do we ensure that this doesn't happen? That is where reproducibility comes in. Reproducibility, it is basically done using something called a seed. So seeds basically say if you give a particular number into the seeds, like I'm giving 0, right? If I'm giving these number to seeds, it says that even if you're sampling from a random distribution, if you're fixing a particular seed number, you'll always sample in the same way from that random distribution. So now if some person is started initialized his neural network using seed 0 or seed 41, and if I'm using the same seed number 41, I'll also initialize my neural network just like the other person has done it. So this is why this is very important, because it will ensure by fixing the seed, it will ensure that your performance, whatever you're reporting, anyone in the world can reproduce those things. So all of these fundamentally do the same thing, but all of them do it for different libraries. So if you want to set the seed in PyTorch, you do torch.manual seed, you give the seed number. If you're doing import random.seed, this is for custom Python operators which are present in basic Python. And NumPy, if you're using NumPy, also has np.random.seed equals to seed brackets seed1. There's a few questions in the chat. Best and efficient way to learn PyTorch. So the best way to learn PyTorch is, I would suggest look into the documentation of PyTorch itself. So PyTorch, when you search PyTorch tutorials, PyTorch official website has bunch of introductory tutorials from beginner level to advanced level, and they're very good. I don't think you need any other than those tutorials. You'll need any other help. That is the best way. But I would say even when you're looking at those tutorials, what will help you actually get familiarized with it, say start coding whenever you're looking at any PyTorch tutorial, whoever is where you're watching, you also parallelly code those particular things. Don't just copy paste that code into your collab notebook or whatever environment and run it. Then you're not learning. Write everything from scratch, just like how it is written in whatever tutorial you're learning. Then that will be very helpful for you to actually understand. When you write it, right, you'll know where you're going wrong. You'll understand what is happening line after the line. So that is the best way, from my experience, I would say you can learn these things. Okay. Second question is, seed value can range. Okay, good question. I'm also not familiar, but I have seen people using a lot of values like 102. I've also seen, I think, 55, random, so many values, but I'll get back to you on what exactly is the range. Typically, you fix any value, like 0 is the most standard, 40, 21, any value you can pick in the smaller range numbers also. But upper limit, I'm not sure what is the exact upper limit for that. I have to get back, I'll get back to you and I'll let you know. Now, this is a custom function which is written by us. You can also write something like this. So this is a custom function set seed, which will set all the important libraries seed values at one go. So you don't have to call them every time. You just write this function. So here you can see, you first select a seed if seed is not given by the user. You select a random seed, and then here, yeah. So if from there you can see, if there is, first you're setting random dot seed, which is Python's custom operators if you want. Then you're setting numpy is random, and if you're using PyTorch also, that is this if condition, you can set all the PyTorch values to a particular seed. Okay, let's maybe ask a question at this point. You are seeing a lot of these things. Torch dot manual seed, you understand. Okay, you're setting PyTorch. What is torch dot CUDA? Torch dot backends dot CUDNN? What are these things? Any idea? Take any guess, post your answers in the chat. What are these things? Torch.CUDA, torch.backends.cudnn. What are these things? Yes, correct. Kushagra has posted in the chat. CUDA is a library or a framework that is helpful to communicate with the GPUs. I don't have to explain why GPUs are important, especially with neural networks. Basically, GPUs are nothing but, let me again reiterate for people who are doing it for the first time, this course. So GPUs are nothing but graphical processing units. You all have your standard laptops, which are most of the laptops, if they are not specifying that they have a GPU, they come with a standard central processing unit, CPUs. That is what we all have been learning from our school days. CPU is the main brain like thing for computers. Then what the difference between CPU and GPU is? A job which CPU does can be done lot of times faster by a GPU because of something called as parallel processing. I won't go into depth. This is not the course for that. Just I want you to understand that GPU does something called as parallel processing, which will do any job that CPU can do much faster because of this parallel processing capability. Now, to actually make use of these parallel GPUs and this parallel processing efficiency, you need a framework or a library to communicate with it. PyTorch has the capability to connect and communicate with this GPU, but it does that with the help of something called as CUDA framework. Now, CUDNN is another framework, just like how CUDA is there, but this is more specific CUDA for deep neural networks. Just CUDA is generic for a lot of things, like not just neural networks, any parallel processing you want to do. And there is again specific to deep neural networks, that is CUDNN framework or library. So PyTorch has again capability to communicate, use these libraries also to make the most out of the GPUs that you have with your particular system. So here they also have some random initializations. So whenever you're training your model with GPU, it's not just your network weight random initializations, but also the GPU system random initializations that can happen. So they also have set their seeds over here. And you can always take a look at what is this benchmark deterministic. So this is goes a lot into the parallel processing. I won't bother it in this particular course. Sorry. Okay. So that at particular function you've written to set all the seeds. This is an helper function. You just can just check whether the seed is working or not. So if you set your seed, then these A and B, whatever you've written, they should come like these values out. So how many ever times you run this, right? Simple function. Each time you run it, each time you should get a and b to this be the same value. If you're setting the seed, if you're not setting the seed, each time you run this simple function, you'll get different a and b values in each time, each run basically. Okay. Now let's go ahead. Again, we have some standard operations like arrange and linspace, same like NumPy, but I'll again quickly go through. Arrange is nothing but it is saying that if you want to create a tensor from the lower range of 0 to the high range of 10, but in the increment order of steps 1, you can do that using arrange function. So it will create a tensor of 0, 1, 2, 3, 4 up until 9. So the last 10th value will not be included. It's the open-ended bracket. Sorry, open bracket for the 10th. It will not include the max range value. So here similarly B also is doing the same thing. np.arrange will also do the same thing. That's what you're comparing. Similarly torch.linspace, it will again, here linspace, what will it do is basically it says that if you give a range and if you're asking it to basically create a tensor of 11 values, but I don't know how those 11 values will come or what the spacing should be between the 11 values. You can just automatically consider equal spacing. That is what linspace comes from. But the range should be 0 to 5. But the values should be 11. That is what this particular linspace does. So that is what you see. It creates a tensor between 0 to 5 having 11 such values equally spaced with each other. Yeah. Then bunch of other operations which you can perform between two tensors, the standard, addition, multiplication, subtraction, all of these happen. So this is what it does. Torch.add, it'll add these two. You can, if you want to save it output in a new tensor also, you can do that. Out is equals to tensor. Multiply also the same way, a, b, out you can put, it'll do the same value. Just moving forward because these are very basics. In the interest of time, I'll go to the actual core neural network concept faster. I'll go there fast. You can do the uni operators also, the typical we- yeah, the typical operators like exponential operators, division, addition, subtraction. Like I said, you can do all those things. Then there are some values like if you want to calculate the sum of your all the values in the tensor, you can use x dot sum. Now, if you have multi-dimensional tensor, you want to calculate sum across only one dimension, then you can do the same command x dot sum. You can specify what axis or dimension. Axis is nothing but the dimension. Axis 0 means it dimension 0 means it will calculate the sum across the rows. Similarly, axis 1 means dimension is equal to 1. It will calculate the sum across the columns. So it can go on like more than 2 also. Like 0, 1, 2 means across the depth. That is the channel dimension if you want to assume, or the depth dimension. You can also do the mean values, some values. I think different operating values are possible. Now comes matrix operations. Typically, if you have operations like these, right, like matrix multiplication and summation or vector multiplication, all of these can be done. Here, a1 at the rate a2 does the multiplication operation, then you add it to a3. That is what is happening. At the rate is like matrix multiplication between a1 and a2. And this is the output which you'll get. You can have three values a1, a2, a3. You send it to that function, and the output which you get is this. Similarly, you can do dot product also. The command is torch dot dot between the two vectors. I hope everyone is familiar with dot product. It is nothing but element-wise multiplication and summation of all these multiplicated outputs. So it's nothing but 3 into 2 6 plus 5 into 4 20, which is 26 plus 7 into 8 which is 56, and then you add up all of them 80. Then comes indexing. How do we index? Just like NumPy, the same process. You can either use one number to get one element as an output. You can have two numbers separated by colon, which will means it will take a particular range or a subset of the tensor. Here it is going from indexing 1 to index 3. You can also have colon 2 minus 2 means from the back the minus 2 elements will come. That is what this minus 2 says. Okay. Then similarly, if you have multidimensional, again you can index column wise or like dimension wise. X of 0 gives you all the values from that particular rows, first row, x of 0 0 says all the values in other dimensions that correspond to first row and first column. Similarly, if you have 3 0 0 0, first row, first column, and first depth channel also, first depth dimension also. And then we have the same flatten operation. So flatten operation, basically, if you have a multi-dimensional tensor, and if you want to just flatten all of them into one dimensional tensor, you can just use z dot flatten. So here examples 2D is going to 1D. This is this will be very helpful with this flatten reshape when you start working with convolution neural networks, which is I think probably week 4. That's where you will see a lot of these flatten operations, and you'll also see a lot of reshape operations that will be very helpful for your implementation. And then after that, we can also do okay, dot shape again, just like NumPy. I didn't tell you about it over here, but just like NumPy, even Tensor have all these dot shape attribute, dot size attribute, dot d type attribute, which is nothing but the data type used for the elements. Yeah, I think these are the typical attributes of what we had for NumPy. Even those will apply for tensors also. Interesting operation over here is squeeze operation. So sometimes you have multi dimensions and you want to reduce one dimension, and you can specify dot squeeze whatever dimension you want to reduce. That will basically remove that particular dimension, and it will give you the resultant new dimension output. But sometimes if you want to unsqueeze, like you want to increase a dimension, that is also possible. That is unsqueeze, and you say where do you want to add that extra dimension. That you can specify the location of that extra dimension. So that is what unsqueeze operation and squeeze operation does. Okay, permutation is basically if you want to swap your accesses, like permuter accesses from, like for example, typically you have image height, image width, and color. But let's say in PyTorch, you'll see in week 4, in PyTorch you want color to be first, then comes image height, image width. So that is what permute will do. Permute will say ki, okay, bring the uh, swap the accesses. Like in this case, here I think we swap 1 to 0. So we're bringing image width, color, and then image height. That is what we're doing over here. Transpose is again the standard transpose which you use in matrices, right? That only works over here also. So I think in the interest of time, let me go to neural networks. Please, these are all shared with you. You can always take a look at it in your free time, all the operations. I've covered most of it, but let me go to the neural networks part. Okay, before that, let's see how the GPU is invoked. That is important. So typically dot device, any tensor dot device will tell you what device this particular tensor is operated on. So when you do x dot device, it is on CPU, but we want to use GPU. First, we have to check if Colab is having GPUs, like in this particular environment, is GPU connected or not. So you can see this is the command to check if a particular GPU is accessing your particular environment or not. Torch.cuda dot is available. This will tell if the GPU is available. If yes, you can set the device. How you can set the device? This is how you set device is equal to CUDA if the torch.CUDA is available, else CPU. So you write the small function set device, and you can immediately you can have this variable device which will give you the device number from set device function, and then you can create all your tensors and send it to that device. How do you send it? When you're creating the tensor, right, you have this option argument device is equals to the device, then it will create the tensor on that particular device. Let me go to perceptron. Now let's first see how to create a perceptron. If you remember, perceptron is nothing but a very simple small version of a neural network where it has inputs, weights, and you do linear combination of those inputs and weights. Then you have the output is sent to some activation function. In perceptron, it is nothing but a sine function, and based on that, you will calculate an output y, and then you calculate the loss between the predicted output and the actual output, and then you do back propagation. No, it's not called back propagation. You basically update your weights with a very simple weight update rule used in perceptron. Now, how do we typically create a perceptron class in NumPy? The flow remains the same. NumPy tensors. NumPy has a lot more calculations. PyTorch will have much lesser lines of code, but the concept or the flow remains the same in both of them. First thing you always need to do is data set. You first create your data set, either custom or download it existing, whatever you want to. But first handle the data set. First sort the data set out. Here, let's see, we are having some data set available in this particular link. You can get that data from this particular link, and we store it in this variable data. Now this data has a lot of columns. From there, you pick the you pick the second column to be y variable, which is your target variable. All the other columns will be your input features. So you created your x and y. You can also convert your y into integer data type, just to make sure that your classes are in integer classes 0, 1, 2, 3, which can correspond to different, like if it's animal classification, it can correspond to dog, cat, etc. You can also, this is nothing, very very simple function. Bin count is basically telling you number of counts, basically class label counts for that particular task or for that particular y. You can always print your x shape and y shape. They should be similar. The number of rows should be similar. Columns will not be similar because x has more number of columns than y. What needs to be similar is the rows. It means that all of the your input x rows will have their corresponding y rows. If there is a mismatch, then it is very important. They'll, your neural network or any neural deep learning model will fail. There should be the same number of x's as x rows as y rows. So if you see, the output is on the bottom. X rows is 100, Y rows is also 100. Now here we are manually shuffling the data set and then splitting into train test. But you can always use scikit-learns or sklearns train test split function. That is also totally fine. You can either do that, or you can either manually do shuffling and testing like we are doing in this particular lines of code. So this is, I think, a standard operation. I will just quickly move ahead. What is important is the normalization part. Can anyone maybe take a guess? Why do we have to do normalization? Any guesses why you have to do data normalization? Please post your answers in the chat. Any guesses? Why do we have to do data? It doesn't have to. It's nothing actually with deep learning. Not to reduce calculations. It is so basically what? No, no, not non-linearity also. So what happens is basically when this is, again, like I said, it is not particular only to deep neural networks, it is to any machine learning algorithm. So typically when you have features, right, let's say your task is to calculate the price of a house, and you have like 10 features. What are the features? Area of the house, location, like a square feet size of the house, location of the house, etc, etc, whatever previous price paid for the house, and all those things. Now, each of these features typically will be in different ranges. Like feature 1 can be in the range of 0 to 100. Feature 2 probably will be in the range of 100 to 2000. Feature 3 can be completely different, like probably in the range of 10,000 to 1 million. Now, when a typical ML model, machine learning or deep learning model takes this, very, very high variance in the range type of input features, it will have a lot of hard time during the training process to calculate which particular feature to prioritize or give more weights, because at the end of the day, if you see, we are predicting what are these optimal weights. It means we are basically trying to say what is the priority of each feature, because these features are multiplying with these weights only, right? So typically we are saying what is the priority of each feature. Now if each of them have different ranges, for the model it's a number. At the end of the day, if it's a higher number, usually it might prefer that to be as a higher value. But that's not actually true, because maybe that for that particular feature, that high number is actually on the lower end of that particular features range. So I hope you're getting my point. Because of these different ranges, the priority or to give to these features will not be correct. So the model will not train fast. It will take a lot of time for the model to reach the convergence or final decision. So okay, maybe let's say with an example. Let's take two simple features. First feature is between 0 to 100. Second feature is between 1000 to 10,000. And now a value at 1000 will be very high with respect to feature 1. But because what is the range of feature 1? Let's say 0 to 1000, and range of feature 2 is 1000 to 10,000, right? So a value of 1000 will be very high for feature 1, but a value of 1000 is very low for feature 2. But for any machine learning deep learning model, 1000 is a number in itself. Doesn't mean anything for it with respect to feature 1 or with respect to feature 2. But if you normalize it, then you're bringing that second features 10,000 to 10,000 also in the range of 0 to 1. Your feature 1 also you're bringing in the range of 0 to 1. Then whatever you have the value, that will be same with respect to feature 1's range and feature 2 range. Then the model can now associate priority accordingly with the help of this number. So that is why usually normalization is done, so that you bring all of these particular features in the same range, such that the model, when it is learning, it can associate, since all of these on the same range, that unit value will mean the same across all these features. So that is the idea of feature normalization. Again, nothing to do with deep learning per se. This is a concept that you need to do even for machine learning algorithms. Now, how do we do normalization? A lot of techniques are available. What is shown is one way of normalization, where you convert into a Gaussian normal distributions usually, which mean 0 and deviation 1. There are other min-max type of scaling or normalization, you want to call that, etc. A lot of different things is there. Okay, then you can plot all of them, and you can see how it is looks. This is how class 0, class 1 looks. Very small data set. This is how the test set looks. And now let's create perceptron itself. So typically, perceptron needs to have all of these functions. What are the main functions? Init function, I'll explain. Let me explain right now. Init function, like the name suggests, it is basically creating all the global variables. Like, what should be the global variables? Number of features, input features, that is a global variable. What should be the weights? What should be the weight matrix that you need to create? The size of the weight matrix. It is nothing but number of features, and output is 1, right? So number of features, comma 1. And like I said, you can create all of them to be 0. That is one way. In neural networks, we do much notices advanced way, where you create random initializations. To be specific, there are actually a lot of research in that also. What is the best way to create? What is the best way to initialize your weights? You can look into that. Um, then bias also, you start off with 0 tensor values, and again the shape is just one value. Forward function, like the name suggests, it will do the forward pass. What is a forward pass in a perceptron? It is nothing but element-wise multiplication and summation of the input and the weight. So in this case, it is nothing but dot product. Dot product is the element-wise multiplication and summation, right? So the dot product between the input x and the weights w plus the bias term. So this is where you calculate the output. Let's call it linear for now. Now this linear will go into an activation function. In a perceptron, it's a simple sine function. What does a sine function say? If it is greater than 0, the output linear. If it's greater than 0, take out the predictions will be 1. If it is less than 0, the predictions will be 0. They're very, very simple activation function. Then you return the predictions. Now backward will do the backward pass in the perceptron algorithm. Again, the backward pass is very simple over here. It just calculates the errors from your predictions, and then these. Okay, so this is not doing the complete backward pass. Actually, here is just calculating errors. The complete backward pass is being done over here. I'll explain. So in the train, we basically have two loops. One is across all the epochs. One is across the values in that particular batch. And ideally, we want to have batch, but since here we have a small data set, we are doing it all entire batch update itself. We're not doing mini batch update. I will show you the mini batch update in the when you go to PyTorch. But here, since we have a small data set, we are doing complete batch update itself. That is why we are running for I in range of y itself. That is doing the entire batch, uh, complete data set. And the outer loop is for number of epochs that you need to run the entire training for. Okay, we first calculate the loss function by calculating the self dot backwards. Yeah, the question is batch size is full. Yes, because the data set is small, right? There is no mini batch or anything. It's basically you're using the entire data set to do the model updates. You're not doing mini batch updates over here. So it's like batch gradient descent in the question which we saw today. That is what this means. Okay. So yeah, then in the for loop, first thing we calculate the loss, which is nothing but errors. And this is coming from the backward function which you just created on the top. What is the input going to that? You give your x input, you give your y input. Once you get the errors from there, this is the weight update rule, which is again for perceptron. If you remember, it's not like the standard gradient descent update. For perceptron, the update rule is slightly different, where you just add with respect to the error itself. Whatever error you had, you just add it to the previous weights and you update the weights. Similarly, for bias also, you update it with respect to the errors which you are getting. So, but if you look into the neural networks, the multi-layer perceptron and all, the update rule is slightly different, where we use gradient descent, which is slightly different from perceptron's update rule. But nevertheless, the flow remains the same. You first send your data into forward pass, you calculate the error from the backward. Now, using this error, you update your weights and biases. That flow remains the same. So once the training will be done, the model is ready. Now you can evaluate the model using evaluate function, where it will calculate again. It will send the model, take the input, send it to the forward of the model, and calculate the predictions. And then you can calculate accuracy using this simple predictions. What at predictions is a vector, your ground truth y is a vector. You just find out where are all these predictions equals to this ground truth y. You sum all of them up, you divide by the total number of values, and that is your accuracy value. So this is nothing but a simple class of perceptron using numpy. Now you can actually instantiate this class, create an object perceptron numpy. You create that, you call the training function, you calculate what are the weights after the training is done, what are the bias after the training is done, and then you evaluate the function. That's it. So very simple way to do. And here we have some visualization after on the train and test plot, train and test data. How is this split? The classifier that is learned, right? How is it splitting the two classes? Is it good or bad? Okay, we can do the same thing using PyTorch, but I'll want to go to neural networks using PyTorch because perceptron is very small. Let me go to the neural networks using PyTorch. So this is the feed forward neural networks, which is multi-layer perceptron. Again, first we created using a numpy function. That is not what we are interested in. Let me go to the PyTorch function. Please look all of these in detail at your own time. Right now, since we have limited time, I'm going a little bit fast. Yeah. Let's come to PyTorch neural network module. This is the most important module that you need to know. So, like I said, NN is the operator called neural networks. Not operator, it is a module called neural networks, which is in PyTorch, which will help you create your at neural networks class. Just like how you created perceptron class, you can create that in PyTorch using these NN modules. How does it look like? This is how typical, let's call this network called wide net. Nothing but a wide neural network. Okay. First, you write your class name. As soon as you write your class name, you need to inherit this parent class nn.module. Very important. If you don't do this, the PyTorch will never know that this particular class is a neural network class. So always make sure that when you're when you're creating a neural network class, always inherit this nn.module. Okay. Once you create, so here in the comments you can see what is the class what is the neural network that we're creating. We're creating a simple one hidden layer neural network. That's the neural network that we're creating. So once you inherit the parent class, first thing is you have init function. Just like how you had the init function previously, here also init function will basically create all the global variables for you. Don't have to worry about weights because PyTorch will take care of that. I'll show you how. All you have to worry about how many number of hidden layers you want. Those are the high level things you have to figure out at this point. Okay, so first is number of cells. This is what I'm saying. Ki number of nodes in your hidden cell that you want. 512 is the thing over here value. It could be anything based on your neural network. So in PyTorch, there is something called as NN.sequential. So sequential is a wrapper, like you can say. So sequential basically takes in all the layers that you want to create, and when you send any input to that sequential, it will start off sending from the first layer. It will send that input to the first layer, get the output, send it to the second tanh, take that output, send it to the second linear layer. So that will automatically happen if you use NN.sequential. So this is one way of creating your neural network. You create all your layers and um, place that inside this NN.sequential wrapper. So input data will go as a uh, whenever you send input data to this NN.sequential, it will send that throughout this entire pipeline. Yeah, like someone has mentioned pipeline. Exactly, it's kind of like pipeline. So it sends it throughout this entire sequence, one after the other. You don't have to manually take the output of one and send it as an input to the other. So very helpful and sequential. But one immediate problem you see is, what if you want intermediate outputs? What if I want, after first linear layer, I want the output to use it for some other operation? That is very normal whenever you're creating your own models. That you can't get easily with an sequential. There, I will show another way of creating. I don't, probably not in today's class. Maybe we'll discuss that in tomorrow's class. Sorry, next week's class. How we can have another way of creating neural networks where we can also access intermediate outputs. But for now, you can think this is the simplest, easiest way to create a neural network. So you create an sequential. Now, the next important function is def forward. So in PyTorch, the only two functions you have to worry about when you're creating a neural network is init function and forward function. You don't have to worry about the backward function that you wrote previously for perceptron. There is a backward function that is written in this nn.module, but typically you don't have to call it or modify it. For most of the neural networks, the backward propagation remains the same. Unless you are trying to come up with your own backward functionality, new back propagation algorithms, you don't have to worry about it. Okay. So see, what did we do in the forward function? We're taking the input x, we're sending it to self.layers. What is self.layers? It is nothing but the sequential. So like I said, as soon as it gets an input, it go through all these layers, and finally from the last layer, it will give us an output, which will return from this forward function. That's it. You created your first neural network in PyTorch. Very simple. In these few lines of code, you can easily create your entire neural network. Now let's actually see and print the how the neural network looks like. So first we set the seed, which is again the same function. If you remember, I just discussed how to set the seed. You then instantiate your neural network class, whatever you want to call it, and then you print. And you can see this is how your typical neural network looks like. First linear layer, tanh, second linear layer. Next, you create your loss function. Now we're going into the final pipeline, training pipeline, right? You have to calculate the loss. How do you calculate the loss? You can use a lot of loss functions available in this NN module. MSE is one typical loss, mean square error loss. You can also have your cross entropy loss, binary cross entropy, softmax cross entropy, all the other losses which are there. You can look into the NN module. So for now, in this particular use case, I'm using MSE loss, and I'm also creating my optimizer. Here I'm using SGD optimizer. You can use any type of optimizers, Adam, RMS prop, Adam, Adagrad, moment, uh, anything, whatever you want to like. Here I'm using SGD, and you can see I'm also mentioning what should be the momentum. So this is SGD with momentum optimizer. I'm also specifying the learning rate, the value I've defined on the top. So once you define this optimizer, you don't have to worry about manually calculating the gradients and updating the weights. It will automatically happen inside this optimizer class. Okay. So in the training process, first you need to always worry about is zeroing out the gradients. Why? Because typically, okay, maybe I'll keep it as a question. Any guesses why do we have to first zero out the gradients before even actually starting with the forward pass, computing the loss and everything? Why do we first zero out the gradients? Any guesses? Question is, why do we have to write this optimizer.zero grad first before even calculating the forward pass, loss, and backward propagation? So this is a training pipeline usually. You do forward pass, you calculate the loss, and you do backward pass. But before doing those, you do something called a zero grade, which basically means you're making all your gradients to zero. But why do we have to do that? Yeah. So reset is obviously we are doing it because we are setting all the values to zero. So obviously it's reset. But yeah, I think the second answer by Tushar, to avoid interruption. Yes, it's not technically to avoid interruption. So what happens is when you're calculating previous loss dot backwards, so it will also calculate some gradients when you do loss dot backwards. This is a loop, right? These four steps happen in a loop ideally. So in the previous time step, loss dot backwards will calculate some gradients. And if you don't zero out the gradients in the next time step, those gradients will interfere and the model will think those are also part of the current time steps gradient and the update will happen in a wrong way. So typically that is a big problem. I would suggest you play around with this, comment this line out, zero grad, and you'll see how bad the results will be like. Model gets affected a lot because the gradients of the previous time step can easily interfere with the next time step gradients and the model can go completely here and there. Always a very good rule is before your training, in every training update rule, always put zero dot grad in the top. That means your training will now function properly. Okay, so once you put that zero dot grad, then you calculate the forward pass, nothing but you send that inputs to your network, you get the prediction as output. Then you calculate the loss function. Then you calculate the loss. Again, this loss function we instantiated on the top, nn.mse loss. You get the mean square error loss. Then you do loss dot backwards. Then you do dot step. So what is the difference between dot backwards and dot step? So the difference is when you do dot backwards, you're basically telling the PyTorch, okay, now you build your entire computation graph. Don't worry if you don't know what computation graph is. Just assume that PyTorch will create all the gradients that it has to calculate for each of the weights. That all will be created. All the partial derivatives, etc., etc. All of those will be calculated by PyTorch at this dot backward step. Then once you do dot step, this is where the weights or the parameters will get updated. So that is the difference between dot backward and dot step. Okay. So once you understood these four steps, let's keep it in the for loop and see. So this is a train function and this is the for loop for. So simple for epochs loop. Again, here we are doing complete batch update because like I said, we're not having a big data set, very small data set. So we're running the entire batch update at a time and we're doing it for n epochs. So first we zero out the gradients. Oh, sorry. First we zero out the gradients. Then we calculate the forward pass by sending the features. We calculate the loss. Then we calculate dot backwards, dot step. That's it. In these simple four lines, your model will get updated and you repeat this for n number of times and your model is trained. Fine, you can keep storing your loss. That is one way. You can store your loss after every 10 epochs, 5 epochs, or after every epoch. That is your choice. Okay. So if you this is where you're calling the train function. This is where you get the losses, and let's plot the losses and see. So this is the final regression. This is a regression problem, by the way. I think you have guessed it by MSE loss. This is the final predictions that you are getting from the regression model. And this is how the training loss is decreasing. You start off with higher loss, and by the end of 1700 epochs, you're coming down. Yeah. So in this very simple way, you created your simple neural network which does the regression task. Again, we gave a simple thing. What we did over here is we used nn.sequential, which is very helpful. But in many times, many big models, when you want to use nn.sequential might not be helpful. We will discuss in the next class what is the other alternative for this. But for now, I hope this is clear how we created the neural networks in PyTorch. Any doubts in this concept of whatever we discuss in the coding part? I've skipped in between some NumPy based calculations of how to do backpropagation from scratch and everything. Please look at it in your own time. Uh, Apart from that, any other doubts you have? Okay. If there are no doubts, then let's end. Yeah, if there are no doubts, then let's end today's session over here. Hopefully by the next week, please go through this collab notebook. If not the NumPy code, at least try to understand how you create a PyTorch neural network and how to do the training in PyTorch, because that is the most fundamental thing you'll have to learn from this week. Because if you're not able to get this, all your other next week's coding or whatever courses you're learning, right, all of them you won't be able to code because you won't understand the basics of creating a neural network class. So make sure you do that, and I'll end the recording for now.